Welcome to qnawire.
Okay, so problem number 23 states that an electron is bound in a square well of 1.50 nanometers and a depth of the potential U0 is equal to 6E1, the ground state of an electron, 6 times the ground state of an electron in an infinite one-dimensional square well. If the electron is initially in the ground level and absorbs a photon, what maximum wavelength can the photon have and still liberate the electron from the well? Okay, so let's start with what we know from the book. So from figure 40, let me rewrite that, sorry, 40.15b, we're given a square well with the potential U0 is equal to 6E1, the one-dimensional well. And in this finite potential well, the ground state electron has an energy of 0.625 times the energy of a ground state electron in an infinite well. So now we can say that the energy of a photon, I'll call it E gamma, is equal to hc over lambda. So the question is really asking, so the question wants to know what's the longest wavelength, but it can also basically, what's the lowest energy photon that can excite an electron from the ground state of this finite potential well outside of the potential well. So in order to do that, the photon, E gamma, must have energy equal to at least the potential of the well, the difference of the potential of the well and the ground state of the electron. So this photon it needs to have at least this much energy to excite this electron out of the well. So if you have a well here, and this is U0, and this is E1, in order to, a photon comes in with h mu, this energy, actually, let me use what I wrote here, E gamma. That E gamma must be equal to at least this energy difference. So U0 minus E1 in order to excite an electron out. So now if we plug that back in here, so let's solve for lambda because it wants to know what the longest wavelength is. So we'll say lambda is equal to hc over E gamma, which is equal to hc over U0 minus E1, where E1 is equal to pi squared h bar squared over 2ml, or which is equal to h squared over 8ml squared, because h bar is equal to h over 2 pi. Okay, so now let's go ahead and plug that in here. We can say, so we know E1 is equal to this, so that's equal to hc over 6 times, you know what? Yeah, that's fine. 6 times E1 1 dW minus 0.625 E1 1 dW. So that's going to be equal to, so this becomes hc over 5.375 E1 1 dW, which is going to be equal to hc over 5.375 times h squared, there should be 1 dW, h squared over 8ml squared So we can simplify all of this. So this now equals, so one of these h's cancel. So this is going to be equal to 8m L squared C. Now remember, this is the wavelength of the photon. Wavelength of the photon over 5.375 times h. So if we plug all this in, so this is going to give us, so this is going to be equal to, so lambda is equal to 8 times the mass of an electron, 9.11, times 10 to the minus 31 kilograms, times the width of the box squared, which is 1.5 nanometers. So 1.5 times 10 to the minus 9. Wow, sorry, not 19. So used to writing that number. 10 to the minus 9 meters squared times the speed of light, which is 3.00 times 10 to the 8th meters per second, divided by 5.375 times 6.626 times 10 to the minus 34 joule seconds. So carrying out all this, you end up with the wavelength, the minimum wavelength, the longest wavelength of light that can excite an electron outside from the ground state, outside of this potential barrier of 6 times the E1 in the one-dimensional well, is going to be equal to 1.38 times, it's supposed to be an 8. Let me fix that. 1.38 times 10 to the minus 6 meters, or 1.38 micrometers, which is an infrared photon, basically. So it has to be, photon has to be at least this length, which is infrared. And the wavelength of the photon decreases when the width of the well decreases, because it's directly proportional here. So that makes sense, which means that the energies, so as the width of the well decreases, the energy goes up and the wavelength goes down.